Okay, let me again welcome the visitors from outside the Physics Department to the department today. As you've just heard, we've just been watching the live announcement of a very exciting development, which is the first practical realization of multi-messenger astrophysics. And a large part of that was played by the LIGO collaboration. So this event today has been called by the UF LIGO group. And the UF LIGO group has been involved in the LIGO collaboration since about 1996 and has been intimately involved. My voice seems to be getting echoey and more echoey. Intimately involved both in the development of the LIGO detector and the advanced LIGO detector, but also in the data analysis. And so the group was involved in the observation of the first binary black hole merger, which was marked with the award of the Nobel Prize in Physics last week. But today we're hearing about something completely different.
The most recent of which was in conjunction with Virgo.
There we go. And so,
there is, of course, another event we were keen to detect today.
So I'm going to ask members of the UF LIGO group to tell you a little bit about what's been going on, and in particular the UF involvement. And I'm going to hand over to start with to the leader of the UF LIGO group, the PI, since the group formed in '96, Gainer Mismarker.
Thank you. So first of all, you heard from David that we are working on that for many years, since '96, more than 20 years by now. And the University of Florida was the third group after Caltech and MIT joining, actually starting the LIGO Science Collaboration, which now consists of many tens of institutes around the world. And University of Florida was the only group which had a hand, besides Caltech and MIT, in design and construction of the initial detector, but of course also of the advanced detector. So University of Florida also had designed some of the data analysis methods, and the method which was designed here was the first to detect the first event with gravitational waves. So it's also one of the largest group in the collaboration. So I have no time to introduce everybody in the group, including postdocs and students who are absolutely critical, as you understand, for what we do. We had many postdocs and students during these 20 years. Some of them graduated, some are professors and working as researchers in other places. Everybody got excellent training, so it's useful for our country. And but today I will try to introduce at least the faculty members who are currently working on LIGO. So first of all, let me start from the end. We anticipated actually that we will come to the era of multi-messenger astronomy. And we have two faculty members who are relatively recent in our group, who are experts in that. So one of them is Imre Bartosz, who is recently hired to the group, and you will hear from him soon. He is responsible in collaboration for writing a paper for neutrino detections, and he's a member of one of the largest of these collaborations. You have heard that for this event, neutrino has not been detected, but useful limits have been obtained. And in the future detections, they will be critical as well. So another is Steve Eikenberry. We are expanded beyond physics department. We have members from the astronomy department, Steve Eikenberry, who is expert in telescopes. And of course, it brings us already close to multi-messenger. So he actually built one of the telescopes which was used for the multi-messenger survey. This, in addition, as a broad expert, he is one of the editors of one of the papers where the expansion of the universe was measured completely independently of past methods, which is astronomy, but now with gravitational waves. So maybe he will say something about that. Then I come to the beginning of this. So the first group included Dave Tanner, who is here, Dave Reitze, who was on the screen, who was stolen from us from Caltech. Actually, he's on leave from University of Florida as a LIGO director, observatory director at Caltech. Then Bernard Whiting, who is probably around, right? And soon after that, we also had Guido Müller working for us initially as a postdoc, but then he became a faculty here. All these people were responsible for the main hardware contribution of UF involvement in LIGO, so-called input optics, which is one of the most complex part of the interferometer. So they designed it and they built it. University of Florida got quite a bit of money because of that. But most importantly, it's a very interesting enterprise. This device was not just built then, it was upgraded and participated in every discovery you discussed, for example, we discussed today. So this contribution is absolutely critical for interferometer. And of course, they were not alone, they were accompanied with many postdocs and students. Then we had one of the recent discussing hardware contributions continuing, Haiping Cheng, who, you know that interferometers are technological marvel, not just challenge, but marvel. And how can you measure with microscopic device the difference of distances in interferometer arms down to the 10 to the minus 3 of the proton size? It's absolutely unbelievable. It's unbelievable to me today, and because I'm not an expert. And so one of the challenges is to, one of the challenges, of many challenges, is to make the coating of the mirrors perfect. And Haiping Cheng is the expert in calculating this. So works in LIGO collaboration, just to show that we contribute to various interesting pieces, and we're all very, very advanced. Now, discussing, is it working now? I'm afraid to forget somebody, so I looked at the departmental website, and we ordered at 10 o'clock precisely, and this happened at 10 o'clock to put up the UF website the press release, the UF press release, which lists some of our contributions. So I don't know if you see anything here. So this is the UF press release called LIGO News. It basically lists at the beginning what you already heard. This is gravitational signal and first optical counterparts which have been detected as a beginning of multi-messenger. So you go further, you see discussion of multi-messenger beginning, and Imre Bartosz and Steve Eichenberry. And then it says that UF is a founding member of the LIGO scientific collaboration. Well, another, in terms of detection, I already mentioned that UF invented the first algorithm which detected gravitational waves, the discovery which was awarded Nobel Prize just about a week ago. And this was invented by Sergei Klimenko, who is here, and myself, with our postdocs and students. So input optics, we mentioned already David Tanner, David Reitze, Guido Müller, and recently we had also contributions from John Conklin from aerospace and mechanical engineering, another person from not from physics who is and now I will try to mention people who are not listed yet. Did I forget somebody from your faculty who are contributing to LIGO? Who? Ah, yes, I should mention that. Actually, he is not a new member of the group. He was working as a senior scientist, postdoc and scientist in our group, but he will join our group in the spring. He already gave his agreement to join. I don't know if he's around. No. Okay, so I think I listed every faculty member. Again, my apologies to postdocs and students who critically contributed to our activities as well. And now I want to give a word to Imre Bartos or to Steve Eichenberg. I don't know who speaks first. Okay. Thank you. So Imre and Steve will discuss the multi-messenger.
Do we have the slides?
We do, but
Clinton's gone. Clinton's here.
We need to switch computers.
Okay. Yeah, thank you. So let me just say that we're going to hear a lot more about the science in a few minutes from the second panel. So the idea is this first panel was the gravitational wave part with a very first counterpart that was detected, that was a gamma ray burst. And the second panel is going to outline everything else that was seen, optical, infrared, UV, radio, X-ray. We've seen essentially everything. So it's a very, very exciting development. And so I don't want to go into details too much on that part. I think Steve will also mention things. I think one of the fantastic things that may be worth emphasizing is this was a much closer collision that we've expected to see. 40 megaparsecs, it's a distance that is more than 10 times closer than the second closest gamma ray burst we've seen. So this essentially means that we've detected a lot more than what we were foreseeing. So it's an incredible story that you see a little outline here from a galaxy, which we know a lot more about now than we did 2 months ago, through the merger of some event to all the way to the collision and the emission of all sorts of radiation. We have we captured this whole process from the beginning to the end. We understand our story very well, again, largely because this event was extremely close. We've seen everything very bright, and also because there were, as it was mentioned, about 70 observatories that actually detected something. Everybody out there, you name a telescope, it looked at this event. It's incredible, from the meter class telescopes to satellites to 8-meter telescopes. Essentially, everybody looked at this event and studied it in great detail. To be honest, none of us knows all the details because many of these other results are coming in now. So if we were not sitting here, I would be reading the papers that appeared 10 o'clock today. So there's a lot of science that we still don't know about, at least within the collaboration. So it's very exciting. It's going to be a few very exciting days to catch up on what actually happened on many fronts. It's an incredible amount of science. So again, even starting, let me just very briefly say, even starting from a very small galaxy, we essentially know what the mechanism was that created the binary to start with from the properties of the galaxy that we saw. It's a galaxy with very low star formation rate. We don't expect large stars to form now, so the system had to live there for a long time, as Vicky mentioned. So it's this binary lived there for billions of years as neutron stars. Then the neutron stars got closer and merged eventually, and we suspect that the neutron stars, after they merged, remained as a bigger neutron star for a while, which is not necessarily the case for every system. So that's something that we learned from the optical observations. As we go on, we saw that there was a emission of very high energy radiation, confirming that this is these kind of mergers are the origin of at least some of the short gamma ray bursts that we've seen. So now we connect the merger of neutron stars to the emission of gamma rays. As it was mentioned, we also now see that there was this gamma ray was observed off-axis, essentially outside of the cone where the high-energy emission is going, which is also something that's completely new. So we have a full picture of this process, which is, again, very exciting, and a lot of new science will come out of this. Again, what you'll see today, there already are some very interesting results, but I think this data and these results will be analyzed and reprocessed for the next months, essentially. And one more thing to emphasize beyond moving on. So we're talking about this one event, and again, there's just one merger, one neutron stars. The fact that this was detected means that in a year, when LIGO turns back on with Virgo, we're going to see this, as somebody mentioned, maybe once a month, very, very often. So this is really just the beginning, and we're going to see a lot of new science coming out of these events, these mergers, both for neutron stars and for black holes that we'll see even more often in 1 year. So again, we're talking about multi-messenger astronomy, not just because of what we learned from this particular event, but because what it promises for the future.
Thanks, Imre. I'm just going to go switch slides here. So I'm Steve Eikenberry. I'm in the Department of Astronomy and Physics. And if I can figure out where my mouse is, I'll put up the single slide I've got. So I'm actually involved in LIGO largely on the electromagnetic multi-messenger side of things, as Imre is as well, largely with neutrinos and also electromagnetic. So I'm actually kind of a little bit ahead of things here because we haven't heard from panel 2 yet, which is going to discuss quite a bit of this, though some of these things have been mentioned. And one of the key results is, of course, as Imre mentioned, the electromagnetic electromagnetic counterpart of this thing, going from gamma rays to radio. What you can see here is the discovery image from the SWOPE telescope, which is a 1 meter telescope. Okay, that's a tiny little small telescope. And that's what actually made one of the discoveries. So this thing is very bright. It's easily observable with even small telescopes because it's so nearby. And sort of my 3 highlights that you'll hear more about on panel 2 in a couple minutes. The kilonova explosions confirmed. So as Imre said, we now know that binary neutron star mergers exist. Yay. We know that they are short gamma ray bursts, as we've suspected for decades, but now we know. And we know that they're associated with these kilonova explosions that were also predicted for about the last 10 years or so, which is neutron-rich material powering through radiative processes, powering the afterglow. And so that's really neat. And hopefully you'll hear, I don't know if we'll hear on the panel, but I'll just point out that Flamingos 2, which is an infrared camera and spectrograph that our team built in the astronomy department here, it's been at Gemini South for a few years now, played a key role on the near-infrared observations for this thing. We also, again, got to see the host galaxy of these things. That's very important. And so we can identify where the binary neutron star came from. And then one of the coolest things from my perspective as an astronomer is we can measure the Hubble constant, the expansion rate of the universe, without any reference to the 100-year-old astronomical distance ladder. So that's something that even intro to astronomy students get taught. You know, how do we know how far away distant galaxies are? Well, we build a rickety structure of different things piled up on top of each other, and we hope it's right. And this relies purely on fundamental physics to get us straight out there to 40 megaparsecs away. And as you're about to hear, the interesting thing is that the astronomers did get it right. They match each other perfectly within the error bars. And that's actually a kind of a cool thing. So there are a lot of things going on with this, and there's even more. For instance, the enrichment of the very heavy elements seems to come, something like half or more from these events. So we'll hear more about that in panel 2. I don't know if we probably have like 2 minutes for questions for anybody who's up here before we switch back to the live feed in DC for panel 2. Laura?
What's the mass of the host galaxy and what's the separation?
The projected separation, I think, is a couple kiloparsecs. 2 kiloparsecs, yeah. And this is I forget the mass. It's an NGC galaxy. It's an S0 at 40 megaparsecs away. It appears like it may be part of a group of galaxies. There's about 10 of them there. It's actually listed in like the 2 mass group catalog as a member of a group. Yeah, it's 4993.
The interesting thing is there's essentially 0 star formation in the galaxy. So it had to be there for a very long time. These neutron stars are not new.
Yep.
A megaparsec is 3 million or a third of a million light years.
3 million light years.
1 megaparsec, yeah. So it's
Yeah.
it's 130 million light years
To this galaxy. Yeah. Yeah. And that does come down to one of the other really neat things. 1.7 seconds is the delay. There may be a real physical cause for that at the source, but that puts a pretty strong upper limit. That means that over the last 130 million years, gravity and light traveled at close enough speed that they separated by at most 1.7 seconds. So gravity travels at the speed of light to a part in what, 10 to the 15, something like that, which is a neat result. Yeah, Dave.
Is there a picture of this galaxy equally good that shows nothing where the red arrow points?
Yes, yeah. In fact, yeah, that was one of our Kendall and I contributed to the discussion early on that the infrared counterpart would have been visible in 2 mass, and so we quickly got out, 15-year-old 2 mass catalog data and said, look, there's nothing there. And there are plenty of optical images as well that show lots of nothing there. And what you can see here again is this is in 4 days. It has faded and turned a lot less blue. And by now you can take pictures again, and I don't know that it's detectable. All right, why don't we switch back then to Washington for panel 2.